Okay, so our next talk is Materiable, Rendering Dynamic Materials Properties in Response to Direct Physical Touch with Shape. It is Ken Nakagaki, Luke Vink, who are our two speakers, Jared Counts, Daniel Windham, Daniel Leithinger, Sean Follmer, and Hiroshi Ishii. And this is also an honorable mention paper, so I'd like to start by congratulating them for their honorable paper.
Okay, good afternoon, everyone. My name is Luke Vink, and this is Ken Nakagaki from the Tangible Media Group at MIT, the MIT Media Lab, sorry. Today we're going to talk about our work, Materiable, and how we can render dynamic material property perception in response to direct physical touch with shape-changing interfaces. Okay, so in our physical world, we have this really rich interaction with materials. When we touch an object, we don't just touch its shape, but also feel it's changed in response to that touch continuously. Our world is rich with these material properties that dynamically inform us about the material's capabilities and limitations. This dynamic physical relationship is something that we wish to bring to computer interfaces. So naturally, the first thing we ask is, how do we bring dynamic material perception to computer interfaces and move beyond simply shape change? So in this paper, Materiable, we propose an interaction technique that allows users to perceive various material properties of rendered deformable materials in response to direct physical manipulation using shape-changing interfaces. So we're going to cover some prior work that we leveraged to develop Materiable. We're going to discuss our approach and a proposed interaction framework. We'll talk about how we managed to build all of this with a technical implementation, where and how we envision this to be used, and how various people responded to and perceived our implementation. Finally, we will discuss how we plan to push this work further into a vision of like actual material computer interfaces.
Okay, so starting from prior work, computer graphic researchers, especially in the community of CGraph, have been developing physics emulation algorithms to render super realistic graphics for different kinds of materials such as water, textiles, snows, or clay. Although every year advancement and quality of these work have been showing us amazing movies or video games, they are limited to visual feedback in screens and displays. To enable to feel the rendered material property in our hand, there have been various kinds of haptic interfaces proposed to provide actual force feedback of rendered material or shape. Although these interfaces are good at rendering actual haptic feedback to our hands, they have limited interaction capability because of their form. For example, on the left side, the Phantom limits us to interact with objects only through grabbing a pen-based device, while others are restricted to glove shape and rigid surface shape. These interfaces also lack the I/O coincidence of what users are seeing and what users are touching. On the other hand, in some research, the actual material property has been controlled computationally to represent virtual materials. For example, in the past in our group, Sean Follmer and Jifei Oh have introduced jamming technique to dynamically change the stiffness of a solid or a sheet-based interface and connect this change to digital contents. This approach enables us to feel and interact with the rendered material freely using our hands. However, the properties that can be emulated in this work are usually limited into a single kind of material property in case of jamming stiffness. So while these physical haptic interfaces requires physical control of accurate force feedback, there have been another interesting approach of creating haptic perception of rendered shape or materiality by combining the touch interaction and the visual feedback. Researchers have proven that such multimodal effect or feedback can convey haptic perception to users without any actual or precise force feedback or texture change. So inspired by this research, we intend to take this further and create a perception of materiality through multimodal feedback effect of tangible interaction with both haptic and visual feedback provided from shape-changing interfaces. Lastly, in the field of HCI, a lot of shape-changing interfaces have been presented. Various approaches have shown us the advantage of these interfaces for conveying dynamic physical shapes that can be felt through our hands and bodies, with also having strong I/O coincidence. However, when we look at real objects all around us in the physical world, they have not only shapes, but also various kinds of material properties. So we aim to push the capability of shape-changing interface to the next level beyond dynamic shape to material properties. So in our work, drawing from the research in the field of material emulation in computer graphics and haptic interaction technique, we introduce a novel interaction for shape-changing interfaces to provide a perception of dynamic material properties. The proposed interaction is general that can be applied to various kinds of shape-changing interface without having the capability of actual force or texture feedback. So this image shows the general interaction framework, which is the core of our contribution in this paper. The framework is composed with the shape-changing user interface hardware and the physics emulation algorithm running on the computer. The shape-changing interface requires a sensor to detect the touch input and actuator to create a shape. As getting a touch input data, the physics emulation render the behavior of certain materiality, and this data is output to the shape-changing interface to create the shape. So as a result, the user gets the visual feedback and the haptic feedback in reaction to the direct touch in the real time. So this combination of real-time bidirectional interaction of touch and visual and haptic feedback through shape output creates the perception of the rendered material property in user's mind. So going to step into the implementation using our technique, using our framework, what kind of materials or material properties can be rendered. So in our work, we developed two kinds of material emulation. One is deformable solid and liquid. Within these two emulators, we were able to create three types of material properties to be perceived: flexibility, elasticity, and viscosity. Through our prototyping process, we chose these three material properties because they can be perceived through the deformation of shape-changing interfaces. Although we believe that lots of you know what these properties mean, we would like to define here because this is really critical through our presentation. Firstly, flexibility is the extent to which a material can be deformed in response to an applied force, which is the inverse of stiffness. So form is more flexible than concrete. Next, elasticity is the ability for a material to resist an applied force to return to its original shape. So rubber is more elastic than clay. Lastly, viscosity is a measure of a fluid's resistance to gradual deformation by shear stress or tensile stress, so often referred as thickness. So honey is more viscous than water. So as for a technical implementation, as for a proof of concept prototype for this interaction framework, we implemented the system using the 2.5D pin-based shape display. Our implementation is composed with shape display hardware and the software that emulates the material properties and also identifies the touch input from users. For the hardware, we utilize shape displays we developed previously in Tangible Media Group. The larger shape display transform was used mainly for our user study, and the smaller shape display inform was used for demonstrating application together with the projection capability. So going to the touch detector, identifies the user's touch input by comparing the value of output height data from material emulator and the input sensed height data from the shape display. So according to the output value shown here in the blue line, a range of dynamic threshold is defined. Then when the input value is out of this range or threshold, the that algorithm defines this as a touch detection. Then this detected touch data is sent to the material emulator to apply deformation in the rendered material. So lastly, I would like to briefly describe the algorithm behind the material property emulator. For both of the material emulator, deformable solid and liquid, we took preliminary emulation techniques based on the virtual spring grid model. Each of the emulators was given different equation based on the Hooke's law for deformable solid and shallow water equation for the liquid emulation. Several parameters for each spring were able to be controlled, such as dampening and spring factors. For the detail of calculation process, we would like you to check out our paper. But most importantly, within these equations, we defined several three variables that can take control of the three kinds of material properties as we described before: flexibility, elasticity, and viscosity. These variables were controlled for the user study, which will be described later by Luke. So this was the implementation for our system.
Cool. So utilizing this interaction technique, we propose application scenarios that leverage this dynamic material perception. So in the fields of education and medical practice, the ability to perceive material properties is not only enhances this experience and understanding of a biological model, but can also guide physicians to problem areas and help to navigate the medical data as well. So for example, medical students can explore different anatomies without the need for an actual human, which I imagine is probably difficult to get hold of. So likewise in education, children can explore various anatomical forms of humans, animals, or plants and get a sense of how they actually feel. In this example, material properties here are useful for testing material combinations. So for example, by combining two viscous types of silicone, the material that forms in the result could be more flexible, and we could use this elastically cured thing to, yeah, you get the picture, whatever. Okay. So here we envision interfaces that combine multiple materials into one interface. We think that this is especially interesting for physical modeling and geoscience. For example, here the viscous water behaves and is interacted with as well as one would expect to with an actual liquid, flowing and responding like a liquid. Whereas the flexible material landscape can be shaped and molded as one might with an actual landscape as well. Lastly, we see the use of material properties as an affordance for interaction. In this example, in the San Jose Convention Center, a stiff material means this building exists already and can't be manipulated, which would obviously prove disastrous right now. So a more viscous material property affords the manipulation of a new building next door. So in order to evaluate this work, we conducted a user study to better understand how different users perceived our interface. So for this, we had 10 users aged 22 to 35 and equally distributed in gender. And in the first test, the quantitative test, quantitative test, where users were asked to rate different random material properties from 1 to 10. In the qualitative test, however, users were asked to describe what these random material properties felt like. So in the first test, our results showed us a noticeable change as we varied each property. Here you can see the given score on the y-axis versus the actual parameter that we changed on the x-axis. Despite not computationally varying the force of each individual pin, our users were able to accurately differentiate these varying intensities of flexibility, elasticity, and viscosity. Also, in the qualitative study, users referred to materials that related to the properties that we actually provided them. Speaking of foam for flexible variations, springy references for elasticity, and water or honey for viscosities. Perhaps most interesting to us as interaction designers is the fact that the way that different users interacted with these materials without our guidance. So on the far left, you can see users attempting to mimic the behavior of the material to get a sense of how flexible or elastic or whatever it is. And then in the middle, we have different ways that people are interacting, not just with their hands, but also their body and even their face, which we found particularly surprising, given that we weren't actually controlling the forces of these. So these users were trying to feel something that we weren't really controlling in that sense. And then lastly, different users were using, for example, one hand to manipulate the interface, and then the other to sort of feel that propagation of that material property. While we understand that there are certain limitations to shape-changing interfaces and pin-based displays, for example, we only have vertical interaction. We can't immerse someone's hands in a liquid or a gas. And we also have limited sensing capability, as we mentioned before, and force feedback, so we can't render the full spectrum of materials with this. However, we think with this particular study, we proved that we can render these material properties to a perceivable level, and we think that this definitely excites us to push this further forward with future work. So in regards to future work, we'd like to add sort of accurate force representation using better sensing and stronger motors. We think this would open it up to lots of different kinds of material properties that we didn't explore here today. We want to look at things like intermaterial interaction, so how do actual materials behave with our simulated versions. And on the theoretical standpoint, we want to look at dynamic affordances, in particular material behaviors that, as we mentioned earlier in the applications section. As we also mentioned earlier, we think that this can be applied to other shape-changing interfaces. We think that going beyond the idea of simply representing a shape and having this bidirectional, continuous interaction with these kinds of interfaces could be really exciting to represent materiality. So in this work, we developed a framework for shape-changing interfaces to enable and design dynamic material properties. We implemented a proof of concept that leverages the shape-changing capabilities of pin-based displays. We represented various application examples that utilize the combination of shape and material perception. And we conducted a user study to evaluate how effective our implementation is with various users. So in the Tangible Media group, we've continued to push shape-changing interfaces throughout the years, moving closer and closer to our physical world. First with Relief from Daniel Leithinger that explored shape change and direct manipulation. Next with Inform, where we explored physical telepresence into material interaction and also dynamic affordances. And today presenting material property interaction as a new method for experiencing more complex bidirectional properties. So we see this work as a first step towards accurate dynamic material interfaces, computers that can be interacted with and behave with the affordances and physical richness that comes so naturally to us in the real world. We see a future where computer interfaces can become just as materially expressive as clay or honey without sacrificing the power of computation. And we see new and exciting other physically impossible types of behaviors emerging from this as well. This vision is in line with our own vision for computer interfaces, and we share this in the Tangible Media group. We call it Radical Atoms. And for this is a vision where we imagine all of this happening to a very extreme, indistinguishable level. Since this project, myself, Ken, and the Tangible Media group have continued to explore property emulation and have some really exciting outcomes. So if you're interested, the Radical Atoms vision was picked up this year to take over a whole floor at Ars Electronica in Linz later on. So we'll show our latest work there, and we think it's going to be one incredible insight into how we envision the future of computer interfaces. So with that, I turn it over to you, and thank you very much.
Well, I have 1.5 questions, if I can. So have you tried out this kind of approach, but with less pronounced squares, with the lower grain kind of change where, I mean, when you said that, for example, you can use it in medical research, it struck me with the idea that, like, a human body is represented by some bunch of squares, which is definitely a different feeling, like it's edgy, it's, you know. Have you tried other surfaces? Or thought about trying other surfaces, which might work in a similar way, but might convey this kind of in-between values? And the second question, which kind of links to that, is have you had experience with kind of playful applications which would, in my opinion, somehow pronounce more the programmability, but also the agency of this so-called material, if we call it like that?
Yeah. So with regards to the first question, our group has explored a lot of different kinds of ways of doing that with sheet-based things. So for example, relief, we applied materials over the top of the pins to kind of change that. So yeah, this could definitely be applied to something like that, and it's certainly something that we'd love to explore to make that a little bit more accurate. The second question, yeah, I mean, for us, it's kind of the immediate thing. Like, all of this is really playful. It's very immediate. And so what we try to do is kind of think about a little bit more specific, hardcore things. But yeah, we're always playing with these things. It's definitely an exciting thing to look at. Yeah.